Hello everyone, welcome to this lecture. So, we will now start discussing about Yau's protocol, and we will first see the motivation for Yau's protocol, and we will see circuit garbling as introduced by Yau as an abstract cryptographic primitive. So, let us first see the motivation for Yau's protocol. So, if we consider the GMW protocol, which is a cryptographically secure MPC protocol, we can say the following: in terms of computation complexity, we require a huge number of OTs to be performed, namely if there are Cm number of multiplication gates in the circuit, then the parties will be involved in n square times Cm number of OT instances to securely compute the cross terms. But now we know that we do not need to actually run those many number of OT instances. Using the help of OT extension protocols in the pre-processing phase, we can run only lambda number of order of lambda number of OT instances, base OTs, okay. And then using the IKNP extension protocol, we can get the effect of so many OTs here, okay, right. And the actual circuit evaluation phase protocol of GMW, once the Beaver's triplets or the multiplication triples are generated, is perfectly secure, because there we evaluate the linear gates in a non-interactive fashion, whereas for multiplication gates just two values have to be publicly reconstructed. In terms of number of interactions, for every layer of multiplication gate during the circuit evaluation phase, the parties have to interact, okay. So, if dm is the multiplicative depth of the circuit, then the amount of interaction which is required in the protocol is proportional to the multiplicative depth. However, it turns out that there are several critical applications where we cannot afford to have a protocol which requires significant amount of interaction among the parties, right. So, for instance, if I take a computation or a circuit or a function where say the multiplicative depth is of order 1000, then the running the GMW protocol for evaluating such a function will require the parties to interact 1000 number of times at least, okay. But if interaction is a critical resource, or if interacting multiple times is not possible, not feasible among the parties, then we cannot run the GMW protocol. And that is precisely is the motivation for the Yau's protocol, because in Yau's protocol the amount of interaction which is involved among the parties is a constant. It is completely independent of the size of the circuit, the number of gates in the circuit, the depth of the circuit, and so on. So, even if you have a huge circuit where say the multiplicative depth is 1000 or 10,000 or 20,000, we require only a fixed amount of interaction among the parties, and that is the best part of the Yau's protocol. So, in networks or in settings where latency is a huge issue, where where the round trip delay is too much, that means it takes enormous amount of time for one message to go to other end and so on and come back, then there we prefer to run Yau's protocol, because there the parties need to talk to each other only a fixed number of time. But the downside of Yau's protocol is that it involves cryptographic operations both in the pre-processing phase as well as in the circuit evaluation phase. So, this is unlike your GMW protocol where the circuit evaluation phase is perfectly secure, but in the Yau's protocol even the circuit evaluation phase is cryptographically secure. It will be secure only when the adversary is computationally bounded, and it requires you to perform cryptographic operations though both in the pre-processing phase as well as in the circuit evaluation phase, okay. So, that is why in terms of computation and as well as in terms of communication it is expensive compared to GMW protocol, but you do a significant saving, not significant, tremendous saving in terms of number of rounds, because it is a constant round protocols. Also, unlike the GMW protocol, a couple of shortcomings which are associated with YAWS protocol is the following. So, first of all, the original protocol was proposed only for the two party setting, and it was only after a significant gap the protocol was extended for the n party case. But unlike the GMW protocol, where the extension from the two party case to the n party case was very trivial, we do not have to do anything. It was simple natural generalization extension. The extension of YAWS two party protocol to n party protocol is not that simple, it is not that trivial. And due to interest of time, I will not be going through the n party version of YAWS protocol, but if you are interested, you can refer to this protocol called as BMR protocol. Okay, BMR stands for Beaver, Micali and Rogave. So, they came up with the n party version of YAWS protocol, but it is not a simple generalization extension of the YAWS two party protocol. Other disadvantage or shortcoming of YAWS protocol is that it is designed only for the Boolean circuit, and research is still going on to make the technique of YAWS protocol useful for any circuit, say arithmetic circuit over a ring or a field and so on. And again, this is not the case, this was not the case for the GMW protocol. The GMW protocol works over any ring, it could be a Boolean ring, it could be an arbitrary ring, it could work over a field and so on. Okay. So, the YAWS protocol for two party case was published in this seminal work. In fact, this is the first paper which introduced the problem of secure computation. So, Yao is credited with the invention of or coming up with the formulation of secure computation, and his protocol was based on this phenomenal idea of garbled circuit, which is also called sometime a scrambled circuit, encrypted circuit and so on. It is a phenomenal idea. Okay. So, even though Yao proposed the problem of secure computation, he also came up with a solution for the two party case. No proof was available, no proof was given in that paper, and it was only later in 2009 where a rigorous formal security proof was given for the YAWS protocol. Okay. So, I will not be going through the proof part of the YAWS protocol due to interest of time, but if you are interested to understand the proof, you are strongly recommended to go through this paper. So, now next what we are going to discuss is the following. We are going to discuss Yao's original garbling scheme, garbling protocol, its optimizations and so on, and most of the slides for the Yao's garbling scheme for secure 2PC I will be taking from my colleague who has prepared these wonderful slides. Okay. So, the notion of garbled circuit or GC was introduced by Yao, but his garbling technique was very specific, and later on this paper by Bellare et al. Abstracted garbling as an independent cryptographic abstract primitive. Okay. And there could be several instantiations of this abstract garbling primitive. We can imagine that Yao's original garbling technique is one of those instantiations, but the advantage of considering or treating the garbling technique as an abstract primitive is that later tomorrow one can come up with various other instantiations of the same notion of garbling, and then one can compare, analyze which instantiation is better, what properties are good in one instantiation, what properties are not good in another instantiation and so on. So, let us first try to understand the abstract primitive of garbled circuit, what exactly is garbling and garbled circuit. So, imagine you are given a Boolean circuit representing a function and it is a well known fact that you take any function, any computation, it can be expressed as a Boolean circuit. In fact, we have the so called universal gates like NAND gate, NOR gates, where in terms of only those gates you can express any given computation. So, if we consider circuit evaluation in clear, then how exactly you will evaluate the circuit. So, if you are given a clear input x and the circuit, then once the input x is given, the circuit is given, you can evaluate each and every gate one by one and then you can obtain the clear output. That is what is the clear evaluation, circuit evaluation in clear, but this does not preserve the privacy of x, we do not want to this done. Now, what garbled circuit do is the following. So, it is a, when I say a garbled circuit, by that I mean a garbling function which will be parameterized by a security parameter lambda, and that garbling function will be a randomized function. Okay. So, it will not be the case that every time you run the garbling function you obtain the same output. So, it is a randomized function. It is like equivalent to your key generation algorithm for encryption scheme, where if you run the key generation algorithm it outputs you a random key. In the same way, a garbling function, an abstract garbling function is a randomized function parameterized by a security parameter which you run, it gives you 3 pieces of information. E is called as the encoding information, D is called as the decoding information, and GC is called as the garbled circuit. Okay. Now, using this 3 pieces of information, encoding information, garbled circuit and decoding information, we can actually evaluate the circuit in a different way. Now, by applying the encoding information on the input x, the clear input x, using an encoding function which is publicly known, we can convert the clear input x into what we call as a garbled input, a noisy version of the input, or you can imagine an encrypted input, but it is not encrypted in strict sense. Okay. So, the clear input x is converted into some other representation, that some other representation is called as the garbled input. And now, given the garbled circuit and the garbled input, we can apply some publicly known evaluation function and get a garbled output. Now, to convert this garbled output in the into clear output, we can apply some decoding function again which will be publicly known using the so called decoding information. Okay. So, now what you can imagine is that you have 2 ways of evaluating the circuit or computing the function output. If you are given the clear input x, then the path that you can follow is this: evaluate each and every gate one by one. But if you do not want to reveal x to anyone in clear, what Yao suggested is the following: you follow the other path here, namely you convert your input x into a garbled input, a noisy version of the input, and give a garbled version of the circuit to anyone who wants to evaluate the circuit. And that person who is going to evaluate the circuit, he will not be evaluating the actual circuit, he will be evaluating a garbled version of the circuit on a garbled input, and he will obtain an output which is completely useless for him, because until and unless I do not give him the decoding information, he cannot convert that garbled output into the clear output. That is the other way of going from x to y, right. So, when I say a garbling scheme, it is a collection of the garbling function GB which produces the garbled circuit, encoding information, decoding information, along with the encoding function, evaluation function and a decoding function. And now this is an abstract collection of algorithms. Okay, it is a collection of abstract algorithms. You can come up with any instantiation of GB, EN, EV and DE, but it has to satisfy certain properties. The way these 4 components interact with each other is as follows. So, as I said, the function GB is a randomized function. It will take the function f, the Boolean function, the representation of the Boolean circuit, and it will output the garbled circuit C, the encoding information E and the decoding information D. Now, any entity who is provided the encoding information and the clear input can apply the encoding algorithm or the encoding function here and obtain the encoded input or the garbled input, which when used along with the garbled circuit in the evaluation function will produce a garbled output, and my decoding function should be such that garbled output along with the decoding information should give me the output y. Forget about this bot here, and this y should be same as f of x, right. So, that is why you cannot come up with any arbitrary GB, EN, EV, DE function. They have to be 4 functions satisfying the requirements that I have stated in this pictorial flow chart, the way these components get involved. Okay. So, now how exactly we can use an abstract garbling scheme to do secure 2-party computation? Well, one of the parties, any of the 2 parties can be assigned as the role of garbler. That garbler can run the GB function, the details of the GB functions is publicly known. So, it can run the GB function by taking the function as the input, and it can come up with the garbled circuit, the encoding information and the decoding information. This is like your secure communication where one of the 2 parties, either the sender or the receiver, runs the key generation algorithm, right. So, I am saying in the context of secure 2PC, let one of the parties, we can fix it as part of the protocol, whether it is the first party or the second party. Any one of those 2 parties can be assigned as the role of garbler, who is going to run the garbling function and obtain the garbled circuit, encoding information and decoding information. And there will be another party who will play the role of evaluator, and he will be provided the garbled input and the garbled circuit. And now he has to evaluate the garbled circuit on the garbled input to get the garbled output, and if we now provide him the decoding information, it can give the clear output back, or it can just send back the garbled output to the garbler, and then the garbler can use the decoding information to get back the clear output of it. So, now you can see that how it helps to get secure 2-party computation done. If we have a corrupt evaluator, will he learn anything about the input? The answer is no, and that is ensured by the security of your garbling scheme. Even though he is provided the encoded information, he do not know the encoding piece of information, namely the piece small e. He knows only the encoded input, he does not know the encoding information E, and hence it cannot figure out what exactly is the input over which he is evaluating the circuit. And in fact, if we withheld the decoding information, not only the input, the output is also remain private from the evaluator, because after evaluating the circuit he only learns the garbled output. It cannot figure out whether that garbled output corresponds to y or y prime or y double prime and so on. Okay. So, that is the way we are going to use an abstract garbling scheme. In the next lecture we will see a concrete instantiation of this garbling scheme. Thank you.